Now we're moving on to problem number 6 from chapter 23. We're talking about mirrors and lenses, and we're told before this next series of problems that we are to use this table that we found in the book. I went ahead and just recreated it. It's a little hard to read maybe, but it's table 23.1 in the book. And so we just have to look at each problem and identify which quantity we're working with and whether it's in front of the mirror or behind the mirror. Okay, so problem 6. A dentist uses a mirror to examine a tooth that is 1 centimeter in front of the mirror. The tooth is 1 centimeter in front of the mirror. So this is the object, the tooth, it's 1 centimeter in front. According to the chart, that's positive. The image of the tooth is formed 10 centimeters behind the mirror. So the virtual image location is going to be behind the mirror. That's Q. Q is equal to negative 10 centimeters. And then we want to determine the radius of curvature and the magnification of the image, right? So radius of curvature is formed by this relationship here. We have the focal length is equal to the radius of curvature over 2, right, by half. So that's how we do the first one. We're going to plug into our formula, right? We have 1 over the virtual image plus 1 over the object distance from the mirror, right? That's 1 over the focal length. So we're asked to find the radius of curvature. We just plug in our values and solve for f, right? So f is going to be equal to r over 2, which is going to be equal to, we're going to take, let's see, what are we going to do here? Invert. So we're going to have q times p over p plus q. Now we have to plug in the values that we had before, which were 1 centimeter times negative 10 centimeters, right? Over, we have, what was it, negative 10 centimeters, negative 10 centimeters plus 1 centimeter. So it's pretty straightforward. Just plug it into a calculator. You end up with negative 10 over negative 9, so it's 10 over 9, right? And since f is equal to r over 2, which is equal to 10 over 9, we take 2 to the other side. R is equal to 20 over 9, which is going to be about 2.22 centimeters. Okay, so that's part A. Part B. Part B, we're asked to find the magnification of the image. We have another formula that we can use, which is the magnification is the negative of the virtual image over the distance from the mirror for the object, right? So this would be the distance of the virtual image. This relationship also is equivalent to the height of the virtual image over the height of the object. But we should just be able to plug in for Q and P. So here we have negative of negative 10 over 1. These are centimeters, right? And this is going to give you 10. So the magnification is 10 times. Okay, number 7. A convex spherical mirror whose focal length has a magnitude of 15 centimeters is to form an image 10 centimeters behind the mirror. So the virtual image is 10 centimeters behind the mirror. And we want to know what is going to be P. Where should the object be placed in order to do that? Then we also want to find the magnification, same as we did before. So this is what we're trying to find. So again, we just plug in 1 over the virtual image distance plus 1 over the object distance is equal to 1 over the focal length. Before we continue, we should just make sure that we have what we need. So we were told that the magnitude of focal length is 15 centimeters. Then we're told that the virtual image is going to be 10 centimeters behind the mirror. And so if we go back to our chart, virtual image location behind and back is a negative value. So we want to make sure that that's negative. So this is negative 10 centimeters. Okay, and then we just solve for p. So 1 over p is equal to 1 over f minus 1 over q, which is going to be equal to q minus f over q times f, which means that p is equal to q times f over q minus f. Right? And so then that's going to be negative 10 centimeters times, what was it, 15 centimeters. Also note here that we actually were told in the problem that this is a convex mirror. And so we know that a concave mirror is going to have a positive focal length, right? So we'll have a focal length greater than 0. For convex mirror, we actually have a focal length that's less than 0. So that means that this actually should be negative as well. So that's something that we should have written down, but we can do it now. Let's see, negative 15 centimeters. So that means, being a little more careful here, we have negative 10 centimeters minus negative 15 centimeters. Right, so 150 centimeters over 5 centimeters, and that's going to equal 30. This is centimeters squared. 30 centimeters. So all I did is just plug into our formula that we're given, right, and solve for the value we want. Just making sure to be careful of the units. This is going to be centimeters squared. This is over centimeters, which gives you a value of centimeters, a unit of centimeters. And also making sure that we double check what it's telling us in the beginning of the problem. It told us this was a convex mirror, so that means that our focal length is less than 0. And we were told that the image is behind the mirror, which means by our chart that this is going to be negative. Okay, then we're asked to find the magnification. So now we have what we need. Magnification is equal to negative of the distance of the virtual image over the distance of the object, which is going to give us 1 over 30 centimeters. Q was negative 10. So this is going to be negative times negative 10 centimeters over 30. Right, so that gives you 1/3, which is going to be about 0.33. So because this is positive, the image is upright, and we also know that it's going to be 1/3 the size of the object, so it's going to be, well, yeah. So it actually gets a little smaller. That's the point. Okay, next problem. Number 11. We're told that we have a 2 centimeter high object placed in front of a concave mirror. So here's our concave mirror. Here's our 2 centimeter high object. And this distance here is 3 centimeters. Just double checking, sorry for the silence, just checking that I'm reading this right. If the image is 5 centimeters high and virtual, what is the focal length of the mirror? So the image itself is going to be 5 centimeters. And we know it's virtual. So not too bad. So we want f. So it's asking us what is the focal length. So recall the formula, right? 1 over q plus 1 over p. Okay, but we're not quite there yet. We need to know what q is. We don't know what the distance, we don't know what the virtual distance of the image is. Or if I say it another way, we don't know what the distance is of the virtual image. We just know the height. But we can use our magnetization, sorry, that's not right, magnification formula to determine what the value of q will be. Now recall that this is the virtual image height over the height of the object. And we are given values for these, right? We're told that the virtual image height is 5 centimeters and the actual object height is 2 centimeters. So that gives us 5 centimeters over 2 centimeters, which gives us a magnification of 2.5. Right? So, using this relation with Q and P, we can solve, right? So now Q is going to be equal to negative P, say 2.5 times P, which P was 3 centimeters away, right? We were told that it's 3 centimeters away. This is our actual object. Okay, so that's negative 2.5 times 3. This is centimeters, and that's going to be negative 7.5 centimeters. Okay, now that we know Q and we know P, we just plug it into our focal length formula and solve for the focal length, which is going to be, again, we're going to have Q times P over Q plus P. Q times P over Q plus P. Okay, that's going to be negative 7.5 times 3 centimeters was the distance. This is centimeters. And then it's going to be over negative 7.5 centimeters plus 3 centimeters. Okay, and that's going to leave us with, if we plug this into a calculator, we get a value of 5 centimeters. Okay, call this a centimeter squared over centimeters. That cancels, leaving us with that unit. Okay, and then I think that's the only thing they wanted us to do. Yep, that's the focal length. That was what we were asked to find. Okay.